let's go ahead and get started. So, how do you find an inverse of a function? Now, we did this the last lesson, but we're going to take it up a notch with some of the functions. As you can see, the first example is f of x equals x squared minus 4, and the second function is f of x equals the cube root of x minus 1. No matter how complicated the problem is, the original function is, it is still very important that you remember those 4 steps that we talked about last week. Remember, you replace f of x with, yes, this pause is, meant to actually happen, okay? I want you guys actually to think about it. You're replacing f of x with what? You're replacing f of x with y, okay? Once you replace f of x with y, you need to, hopefully you remember to say switch your x and your y. Okay, definitely make sure you switch x and your y because we're finding the inverse. That's what finding the inverse does. You switch x and y. After that, you had to solve for, hopefully you said y. Okay, and then of course after you're done doing the algebraic processes, then of course you want to make sure that you replace y with the correct notation, which is f to the negative 1 of x. Or if it's g, you replace it with g to the negative 1 of x, and so on and so forth. It just depends on the function that you're actually, what you're actually given. So let's start here. So step 1, we're going to replace f of x with y. Then we're going to switch x and y, so this becomes x equals y squared minus 4. Then we're going to go about solving for y doing the algebraic processes. So to get y by itself, we need to add 4 to start with. So the x plus 4 equals y to the second. And then hopefully you guys remember how to get y by itself. We're actually going to take the square root of both sides. So then we'll have the square root of x plus 4. And then we'll go ahead and add in the notation of f raised to the negative 1 of x. Okay, let me add in the square root. And that is the inverse. So it still applies the same way. You just want to make sure that, whatever you need to do to undo, to get y by itself, then you just make sure you, follow proper things. If you are squaring something, you take the square root. Multiplying, you divide. Subtracting, you add. Okay, remember everything's the opposite. Now I want you guys to try number 2. Try writing the inverse. So pause this video, write the inverse, and then press play when you're ready to see the answer. So hopefully you have an answer, okay? Hopefully you switched f of x with y. So then it would have been y equals the cube root of x minus 1. And then from there, you had to switch x and y. So when you switched x and y, hopefully you got x equals the cube root of y minus 1. After that, you had to solve for y. Now, to get rid of a cube root, hopefully you cubed both sides. Just like to get rid of a square, like in the last problem you took the square root. Well, to get rid of the cube root, you do the opposite, so you cube it. And then after that, you add 1 to both sides, and you get that to equal y, but I'm going to go ahead and put in the inverse notation because that is my final answer. Okay? That is my final answer. So rules still, they still stay the same. You just want to make sure that no matter how difficult the function is, you're still going about those 4 steps. All right? So what is a one-to-one function? Now this is some new terminology here. Last time we talked about what it meant to be a function. Remember, to be a function, there are no repeating x's. Every x has a unique y. Okay, it also, remember we also talked about the vertical line test. These are all things to be just a regular function. Now we're going to talk about what it means to be a one-to-one function. So what is a one-to-one function? It's a function which every element in the range of your function corresponds to exactly one element in your domain. So this is the exact opposite of to being a function. Remember, To be a function, every element in the domain corresponds to exactly one element in the range. So in other words, your x's didn't repeat. Well, to be a one-to-one function, now your y's can't repeat. All right, so if you take a look at these examples that are here, as you can see, this first function is one-to-one. Okay, and you can look at the table right here. Every single y value is different. There are no repeating y values. All right, no repeating y values. So that's why this one's one-to-one. The second one, this quadratic looking function, it is not one-to-one because if you notice, your y's repeat. Okay, your 4's repeat, your 1's repeat. So in order to be one-to-one, your y's cannot repeat. To be a function, your x's should not repeat. Okay, so if I go back and look, the very first function, this is a cubic function, none of your x's repeat. So this is also a function. It's not just a one-to-one function, but it's also a function. Here, none of your x's repeat. This right here is an example of a function, but as we can see, it's not one-to-one. Here's some mapping diagrams. That's what these are called down here. These are called mapping diagrams to help you kind of see exactly a little bit in a different way what it means to be one-to-one. As you can see, none of your x's repeat. None of your y's repeat. You have one unique x for one unique y. That's what it means to be one-to-one. Here, none of your x's repeat, but as you can see here, x1 and x2, they both go to the same y value. So this would be a function because none of your x's repeat, but it's not one-to-one because y1 actually goes to x1 and x2, which can't happen. And this one here, this one's example of not being a function because as you can see, x1 will go to y1 as well as y2. And you know, these basically correspond to numbers. So if this is 1 and this is 2, this is 3, 4, and 5, these basically represent coordinates. Okay, they represent the coordinate 1, 3, 1, 4, and then 2, 5. Okay, so mapping diagrams are nothing but different ways to represent ordered pairs. And as you can see, when I write it like this, yes, our x's repeat, which cannot happen, which means it's not a function. Now, some of you guys might say, well, it's not a function, but it's one-to-one. The only way that you can have a one-to-one function is it had to be a function to begin with. The only way to have a one-to-one function is that it had to be a function to begin with. Okay? Please make sure you make a note of that. The only way to be a one-to-one function is that it was originally a function. So, the vertical line test helps us determine if we have a function. The horizontal line test will let us know if it's a one-to-one function. Okay? The horizontal line test will let us know if we have a one-to-one function. So, if a function that's given to you, if it passes the horizontal line test, then you automatically know it's a function and it's one-to-one. But if it doesn't pass the horizontal line test, we know it's not one-to-one. But you still need to check with the vertical line test to see if it is indeed a function. So, the inverse function. Let's continue talking about it. The inverse function. If a function is one-to-one, then we know the inverse is a function. Okay? So, if it passes the horizontal line test, if none of the y's repeat and it was originally a function, then we know that the inverse is a function. Now remember, the inverse is where we take the coordinates of a function, x and y, and we switch them. Okay? So the x coordinate on the original function of 0, -1 is going to get switched to represent the coordinates on the inverse. So if 0, -1, if f of 0 equals -1 on the original, then f to the -1 of -1. So on the inverse, if the x is -1, then we know the y is 0. Okay, because literally all the points do, they're just switching. So the x on the original is the y on the inverse. The y on the inverse is the x on the original. So if on the original function the x coordinate was 1 and the y coordinate was 1, then on the inverse the y coordinate is 1 and the x coordinate is 1 and the y coordinate is 1. That one's kind of an easy one because we didn't change the numbers. But let's look at the next one. If 2, 3, x is 2 and y is 3 on the original, On the inverse, x is 3 and y is 2. So literally just taking the points and switching them. And remember, that was one of the ways I told you guys could graph the inverse function. So take a look. You have 1, 1, negative 1, 0. Then you have 3, 2. Okay, these are all points on the inverse. So this line right here represents the inverse function, and this will represent the original function. We're literally taking the points and switching them to get the graph. And hopefully you can also see as well is that this is a reflection over the line y equals x. See if you guys can see it right there. All right. Now, remember, in order for a function to be one-to-one, it has to be a function to begin with. If we take a look at this picture down here, we can see that this is not a one-to-one function because it does not pass the horizontal line test. It hits it at 2 different points. So when this happens, when a function is not one-to-one, we can make it one-to-one by restricting the domain of the function to find the inverse. Okay? When you restrict the domain of the function, then you basically are able to find the inverse function. So if I were to take this quadratic and just not even consider the x's that are less than 0, but instead look at the domain from 0 to infinity, then we can see that just that part, just that right side, that right-handed part of that quadratic will indeed pass the horizontal line test, meaning that it would be a function. So if we're able to restrict the domain, then we're able to answer all these questions and actually figure out the points on our inverse. So if the coordinate is 0, 0 on the original, then it's 0, 0 on the inverse. If it's 1, 1 on the original, it's 1, 1 on the inverse. Those are the easy ones. But if it's 2, 4 on the original, then it's 4, 2 on the inverse. And as we can see on this graph over here to the right, you have 0, 0, 1, 1, 2, 4. This right here represents the original function. But once we flip them, 0, 0, 1, 1, 4, 2, this represents the inverse. And yes, it's still a reflection over the line y equals x, which goes straight through like so. When you're reflecting over that line, it's like you're pretty much taking your paper and folding it on that line y equals x. And last but not least for this foldable, we're going to prove that functions are inverses. Now we talked about how to actually find the inverse function, but now we're going to prove that functions are inverses of each other. Okay? So if you're given two functions, you'll be able to determine if they're inverses of each other by doing this right here. Hopefully you haven't forgotten what that means from your last unit test, but remember the open circle means composite. So if you do f of g of x and g of f of x, and you want to do that, you want to actually figure out what that composite is, okay? So let's start off by doing f of g of x. And if you remember from composite functions, f of g of x basically means I'm taking the g function and plugging it into the f function, okay? So everywhere I see an x on my f function, I'm going to plug in g. Okay, so I'm going to replace x with a parenthesis for right now. And now I'm going to plug in the g function. And I am typing this on a computer. As you guys can see, I'm using the keyboard. So that's why I have to like break it into these pieces. So just bear with me. All right, I have plugged g into f. And now what we're actually going to do is we're actually going to go ahead and simplify this out. So of course, anytime you have a number on the outside of set parentheses, you want to distribute. So 2 times 1/2 x just becomes x, and 2 times negative 3 is a negative 6, and then we just bring down that 6 that was already on the outside. And as we can see, if we continue to simplify, we will have just x. Let's do the other way. Let's do g of f of x. So now I'm going to plug f into my g function. So everywhere I see an x, I'm going to plug in everywhere I see an x in my g function, I'm going to plug in f. So again, just bear with me because I am typing this up. So I have to insert in the 1/2 because I can't really do fractions like that. Okay, so g was 1/2 x minus 3, so I'll replace that x with a 2x plus 6. And again, I'm going to distribute that over, so half of 2x is x, half of 6 is 3, and then I bring down that minus 3 from before. And again, we see that once we combine like terms, it just equals x. If the two functions are inverses, then f of g of x and g of f of x will equal x. Please make sure you put down that it equals x, not that it equals the same thing. Those are two different things. They both f of x, f of g of x, and g of f of x, they both have to equal just regular old x. Plain old x, not negative x, not 4x, but just regular x. If it does, and you have to do both of them, if it does, then you know that they're inverses. If they don't, then they're not inverses. And yes, check both ways. Do f of g of x and g of f of x. Just don't do one way, because sometimes it could work for one, but not the other. Okay? So hopefully you understood this video. You're going to get another sheet that I want you guys to spend some time working on. Actually work on those problems, all right? And then I want you to check out the other video that actually has the answers already worked out for you. So you can basically check your answers and see how well you did, all right? And then, of course, bring any questions you have to the next class.